Hello, we're back and we're doing a second part of our talk about the bytecode interpreter and of not just a talk, but actually coding one. And I thought since last time I basically just kept talking and talking about how you would do a function call, that this time we should actually implement it. And before we do that, I wanted to show it more graphically to maybe help people a little bit better to understand what we're doing here. So basically, since our bytecode interpreter is basically a simulation of a CPU, function calls in a bytecode interpreter work the same way as they work in an assembler. So if you've ever learned assembler programming, or if you now go out and say, hey, I didn't get what Uli said here, maybe someone else can explain it better, find a tutorial how to use assembler and how to do a function call in assembler. Maybe that will explain it in a way that is more suited for you. So what I'll be doing here is basically just showing you different parts. So this part is basically the CPU or our registers struct that we have in our code already. So we have current instruction as one field in there, and that contains the address or array index in our bytecode interpreter's case of the... No, actually we have the address in there, yes. So the address of the current instruction. So these pink boxes down here are basically individual instructions, 3. There is one before the call. Whatever that does is not really important for us right now. Then there is the actual call instruction, and then there is one or more instructions after the call. And then we have the stack pointer. In our bytecode interpreter, that is actually all one bit, like the stack and the stack pointer are just a C++ vector. In a real CPU, what you actually have is you just arbitrarily decide that the stack should start at a certain memory address. Let's say just, 0 at the start of the first RAM chip if you want to. So then this, our variable x with the value 42, the slot on the stack for that would be at address 0. And assuming that this is an int 16, as we always had, so at address 2 would be the next thing. We do not have anything after that. So these are just empty boxes I drew, so I wouldn't have to draw them later. But that's basically the space we have. And so what you do is just you remember where would the next element on the stack go, and that's what the stack pointer is. Again, the vector takes care of that for us, so we don't have to do that, but that's how it works in a CPU, so I thought I'd use the same name here. Because we will actually need something like the stack pointer later, and so it helps to know that the stack pointer is usually already there on a real CPU. Alright, so we want to call a function. And as I mentioned, there are several parts. Whoops, sorry, bumped the microphone there. So as I mentioned, there are several parts to calling a function. One is getting the return value back from the function. The second is passing values into the function, parameters, arguments. And then, of course, there is redirecting your code, jumping to the actual first instruction of the function and going back there. And as you may remember, our problem here was if we just hardcode in our function's instructions that x is address 0, that means if that function calls itself recursively with different values, that then it would overwrite the outer calls x. So we need a second x in a different location. So how do we keep track of that without, like needing a new copy of the code with a different address in it? And how you do that is you introduce the so-called base pointer. I've prepared that here before I moved stuff. Okay, so not really that well prepared. Okay, so base pointer. The base pointer is just a pointer to a spot on the stack, just like the stack pointer. It starts out as basically 0 or whatever. So let's see. Let me just do that. So it points to 0, to the start of the stack when we start out. And that means, and what we do now is we use this base pointer to say we write all addresses of our variables relative to that base pointer. So we introduce extra instructions. So instead of load int, we can say load int base pointer relative. And load int base pointer relative will take whatever number you give it, so 0 for our variable x, and add whatever the base pointer is. So for the first call, of course, that would be 0 plus 0. So we would get the address 0 where the 42 is. Once we do a second function call, it will reserve more space on the stack for its x. I don't know, can we call that x2 maybe? Let's see, can we make that smaller? Yeah. So we have an x2. And so what we have to do is, let's hide that for a second again. This is how it starts. When we call a function, the first thing we do is we take whatever is in the base pointer currently and write it on the stack. Which is actually, let's reuse that. Okay, and so in our case, the base pointer was 0. It's fine, if we are 3 levels deep, that would be, 4 or whatever. So just assume this is a number, but in our example right now, at the first time, it's 0. So we write that on the stack so we can remember it before we change the base pointer. And now what we do is we change the base pointer so it points to the end of the stack. So that means all new variables will start here. And then we do we can reserve our space for x2. And whenever we ask base pointer relative 0, it will say, okay, base pointer is now 0, 1, 2. So it will add 0 to 2, which means 0, 1, 2 is actually the slot it will give us. Perfect. So that means our code always just says base pointer relative 0 and doesn't have to care that that actually turns out to be 2 in the second case. And, that would be a different number here. Who cares? And then, once our function is done doing its thing, what it does is first, it cleans up its... oh yeah, and of course the stack pointer would update as well and would be pointing back here now. Let's hide that. So the stack pointer would now be pointing here, of course, because that's the end of our stack. Anyway, and so when we return, what we do is first we clean up, we remove the space we used for x2 because we're now done doing whatever we did. And then we take our 0 off the stack and write it back into the base pointer. So that means we remove this and set the base pointer to 0, which will make it point back here, because that's the start of the 0th block. And of course, we will be updating this. The stack pointer will automatically update because we popped 2 elements from it. So that's what the base pointer is. It's just so we get a new copy of our variables, but identical code. And we just set the base pointer to the current stack pointer after we pushed it. That's why it pointed here, I think, is where it pointed, because we first pushed the 0 to save it and then replaced it. That's all we do here, basically. And why we need a base pointer, and that's called base pointer relative addressing. It's a thing in, real CPUs. What else do we need to do? Well, when we call a function, I said, what do we do? Well, a call needs to know what to execute. So if we have a second function, or if we have our function here, so that is, I don't know, just does A, B, C. Make that italic because they're not real instructions. Oops. Okay. So that is our function, and this one calls this. So this instruction has the address of this function, of the first instruction of this function written into the instruction. That might just be the index, or it might actually be the, like usually it is the full address, because you remember we can compile several parts of a program in different memory blocks, and then and we still want to be able for one to call the other. So either we would need a pointer to the array and an index, or we just take the address of the element, which in C we can do. In a language like Swift, where you can't actually use pointer arithmetics, you would actually need to say, okay, here, keep a pointer to the array and an index to add to it. But, same difference. It's just you don't do the addition right away, but rather you let, Swift do it in that case or whatever. But anyway, in C and C++, we can just, keep pointers to random elements, so we're fine. All right, so what happens here? What we want to do is, we've already had a jump instruction, which was very easy, because all jump did is it changed the current instruction to the next instruction to execute. The problem is when we're here at the end, and we need to somehow go back. So let's say we have a magical return instruction here that is somehow supposed to go back to this next instruction. How would it know how to do that? That's our big question mark here, this arrow. So how do we do it is, at this spot, we still know what the next instruction will be. It's current instruction plus 1. So what we do is, when we call this and push the base pointer, the old one, on the stack, we also go and push the next instruction on the stack. And that is what we call the return address. So, assuming this starts at 0 and every instruction is, I think in our case it was 4 bytes. So that means we have 0, 4, 8 is the offset of the after instruction. So we push 8 on the stack. So that points here. And the return instruction does the things I mentioned before. First, it takes the 8 off the stack and writes it into current instruction. So that means current instruction then no longer points to the call instruction, or rather no longer points to the return instruction at this point, but rather is bent to point here. Let's hide that one as well. We don't need that anymore. So we just changed the current instruction to be after, which is exactly what we need. So we've popped this off the stack. It's fine. Then, since the return instruction also knows that we need variables, it's also the instruction that takes care of taking the old base pointer off the stack and writing it back into the base pointer variable. So we're back here. So that's the job of the return instruction. And of course, the call instruction, as I said, is the reverse. So the call instruction first pushes the base pointer, the return address, and then actually changes the current instruction to the first instruction of our function. That's what we do. And that's basically it for calling a function. Again, the whole point behind this is to allow recursive calls. If you knew that at the same time your function would only be running once, then of course you would not need all this. And that was also why when the first procedural programming languages came out, many assembler programmers, which, was the only kind of programmer basically that existed until then, went, this is inefficient, this is wasteful. Because, like in many cases, you have functions that will never be called recursively. And so why would you bother setting up the stack for this instruction, setting up a base pointer in that register? Those are all wasted cycles where the CPU is just moving data around that is never needed. So, like when you hear today that, I don't know, functional programming with its map reduce ideas or whatever is totally inefficient, think back to that. The same complaints existed about assembler. Today, most people use procedural or object-oriented programming languages as the minimum baseline, and the only people who write assembler code are mainly people who have a good reason to do so, so who write a certain piece of really, really performance-critical code that needs to, get every cycle out of the system, or they write, otherwise very low-level code that needs to, talk to certain hardware or something, and therefore cannot really be done in C. But that's basically it. Anyway, so much for preaching. Now let's go back to our code and actually implement this as promised. So as I said, we have a bunch of instructions that we will need. First, we have load int and store int. So of course, we now need load int bprel, so load int base pointer relative. You could actually, I shouldn't, but I'm lazy. I should just write those out and call it base pointer relative. My IDE autocompletes, But anyway, somehow I find this pretty, so I guess I'm going to do it for this tutorial. No, let's write it out. Come on, let's be... And let's do the same thing for LT. Well, that should be less than, but I guess that ship has sailed. Okay, so those are what we need to actually do load int and store int for variables without being in danger, of overwriting our own data. And now what we also need is a call instruction and a return instruction. All right, so far so good. And now we need to go to our bytecode interpreter header, because here we don't just need a current instruction, we also need, and I'll use the type size t for that, for the simple reason that our stack uses that type for its elements. And why is there a space here? Okay, and so this is our base index. I'm not calling it base pointer because it's not actually a pointer, because our stack is owned by C++ and we only have indexes. Every time we push something, like in a real CPU, you reserve memory. Like usually what you do is like your program uses memory, say, from the start of the lowest level RAM chip, and your code uses memory from the top or the highest point of the your stack uses memory from the highest point of the RAM chip. Or maybe what they sometimes do is just they say a stack can only be at most like 500k or something, and then you just say, okay, 500k divided by 2 would be 256 elements is the maximum elements this vector can. And so they would just reserve 256 bytes. That would actually be bytes, not kilobytes. So 256,000 roughly bytes. I don't want to multiply by 1024 now. But you just pick an arbitrary number that is enough for most users, and then the reason why you would do this is because if you have multi-threading, then of course each thread needs its own stack. Because if one stack and the other stack, you can only put stuff on the end of the stack. So one thread wouldn't be able to push anything onto a shared stack when another thread is actually just using it, because you might be interfering with each other. So they need separate stacks so they can mess around with that. And so you would just say, okay, the first 256 bytes is the first stack, and then after that is another stack, and things like that. And your stack doesn't actually use all of that, and that's why you can use a pointer to indicate the end, because you've already reserved those 256 bytes of memory, and all you need to know is keep track of how much you've actually used of that. But since we have, this is all on the heap, really, this is just a simulated CPU. Here we can just say make it larger and it will move it around. So we cannot keep an address to an element inside our vector, because the address of elements can randomly change. So we just keep a base index which points into this stack, long story short. Also, I've started talking about things like heap. Basically, the heap is memory that is not on the stack. So this programming language doesn't have heap. This simulated CPU doesn't have a heap right now. It only has a stack. That's fine for our simulation purposes. So I'm not going to say much more about the heap, except that, you can just ask for, I need 4 kilobytes of heap memory, and it will just give you a memory address and say, here, starting at this point, you have 4 kilobytes. That's what malloc or new in C++ do, for instance. Those are the things that do heap things. But that's not really relevant, so I shouldn't get sidetracked. All right. Anyway, we have our base index here, which is our base pointer that I mentioned here. That base pointer is the base index. We have that now. We have a call instruction. We have a return instruction. And we have load instructions. All right. And so now let's go and where do I open and write split? Okay. And actually my webcam is not covering anything right now. That's good. Or nothing important at least. Okay, so now we need more functions. 2, 3, 4. The first instruction is load int base pointer relative and store int base pointer relative. And then we have call instruction and return instruction. Wish I could type. All right, so we have those functions here. We've declared prototypes for these. And now I think each of these wants to be implemented, which I think I can just generate definition. Yes, it will just do it. Nice. I'll have them all in here. All right. Wrong button. Okay. Generate definition. Load int, store int. Call. And return. All right, so now we have our functions, and now we also need to copy this stuff into our array of instructions, of course. All right, so now we have done all the boring housekeeping that C and C++ make us do here. And now comes the actual work. So first, load int. Did I just accidentally hit the insert key? Or why is the cursor? Okay, my cursor is suddenly a block cursor. Don't ask me why. Not a fan. Can I just close it and make it open again? Okay. It's the IDE is smart, but sometimes it still surprises me and I can't Google for what that was right now. Okay, so we already have load int and store int instructions. So all we need to do is copy their code and add the base pointer. So stack current instructions P2, that plus registers base index. And the same here. So that way we don't have to actually specify the base index. Funnily, we won't really be using the undecorated base integer load int and store int instructions anymore. So we could have just changed the existing ones, but you know, since in general you want to be able to also, like if you have global variables, then for those you would use the regular load int and store int instructions. Because what you would just do there is at the start of your program, when your main function starts up, you would say, okay, now define, reserve some stack space for these global variables or something. Well, in a single-threaded program, you would do that. Otherwise, you would, you know, reserve state somewhere, space somewhere with an actual address. All right. Call and return is what these are. And now, what do we do? So call is basically the same as jump by. So that means we take an address and jump to it. So our call instruction here will be relative, just because that's what jump by is as well. We could also make it absolute with the actual memory address, but that would make things a little more difficult for me in our main function to actually come up with the right address. I would have to find that out and fill that in. So I'm just going to do it relative for now. But as I said, you could use the pointer, it's just some extra work. Okay, so what does call do? Remember, we have registers base index, which we want to push on the stack. So registers stack push back. Now, of course, you see this is where our past decisions come to haunt us. Base index is a size t and not an int16. So we have to typecast here. Danger, jump address is limited to 16 bits. Or rather to 15 bits even, because it's a signed number. No, actually it's 16 bits signed, because we can jump up or down. Anyway, so also what we want to push on the stack. Now we're screwed. Okay, so here is where our problem comes in. We currently have int16 as the only type we support. In a real CPU, you would have arbitrary sizes of items on the stack. You wouldn't just have it limited to an int16. But here, we actually need to push a memory address onto the stack. So, how do we do this? I think the easiest way right now is for me to just change int16 again. Or what do we do? Let's... Okay, registers. So first, theoretically, we would want to do registers current instruction, right? That's what we would want to push. The problem is, how do we do that? I think I'm gonna do it a shortcut. Like usually all of this ends up on the same stack, which is fine. But I'm just going to be mean and say, hey, I'm going to add a return address stack, and that is a vector instruction pointer. Come on, no. Return address stack. All right, so doesn't matter. We can just make up stuff here because it's our own simulated CPU. So this way we don't have to worry about different types. We could have separate stacks for int16, for double, for instruction pointer, for object pointers, for any type we want, if we want that. We just have to then be very clear about if we have, load. We have load int instruction here. So of course, if we had a load double instruction here that gives us a floating point number from the double stack, then of course we would have to make sure to remember that this is a completely different stack. So 0 stack index on the double stack that you give to load double instruction is a completely different variable than the 0 int variable on the int stack. But okay, that's fine. So we have the return address stack, and we push our address on this. We could do the same for the base index, but since that's just an index, the numbers are going to be small. So I can just get away with this. So we've pushed these two values on their respective stacks. And then we've jumped to this instruction. And again, this is safe because it will first evaluate argument 2 of the current instruction. And then it will add it to the current instruction thing to perform the actual, to the register to perform the actual jump. Also, we shouldn't forget, if you remember here, what we're actually saving is not the address that we are at. It's the next address. So it's 0, 1, plus 1, 2. That's the address. And then 3, 4, 5. Would be what we want to. Okay, so we say plus 1, because remember this is typed as instruction, so plus 1 is enough. It's the number of instructions. And now the return statement has to be the reverse. Since these are different stacks, it actually doesn't matter that much. If these were both on the same stack, then of course you would have to first remove the return address. And then that. So we just assign this here, back, and then remove it, pop back, and then we do the same for the base index. So base index equals register stack back. All right, and again, pop back. Whoops. All right, so that means we've restored the, or rather we've restored the current instruction. That we saved here, or here rather. So we restore that, and so that's current instruction plus 1, which is the after instruction here. So that address is now written back. Then we've removed that from the stack, so that, if we several times have to return 3 times, we each get a different return address, and we're not stacked at the same one, of course, which we would be if we forgot to remove it. So if you get any endless loops or something, check if you maybe forgot to remove anything from your stack. And then we do the same. We get the base index from the stack and remove it, which means that function that we've returned to also gets its local variables back and not the ones of the function it called. So that's basically it. And in this step here, we've already done the reverse of this last instruction. We've already assigned the current instruction. So you have to be careful here, though. If you do it this way, that means the return instruction cannot have any arguments, because at this point, you're on whatever arbitrary instruction follows the last call instruction that you return to. So that's not your current instruction. So maybe a better way would be return address, and then we say instruction return address, and that way we still have our current instruction. So let's just, do defensive programming. Restore the base index. I hope we won't need them at this point. And then here, just like we have it here, as the last step, restore the current instruction. Or rather, change it to the return address. So that's really all that these things have to do. And now, of course, we would have to change our code to actually use this. So right now we have a nice loop. So first we push X. That reserves our stack space. Since that happens at the start of this function either way, there is really no, reason to change this. It will just create a new variable, and if there is already, a variable and a return address, so a variable X from, the surrounding call, and the base pointer and the return address, if those 3 are already there, then we're fine. And now instead of load int, we of course have to say load int base pointer relative. And here as well, base pointer relative. Push int, add int, and here store int base pointer relative. So all of these will now operate relative to the base pointer. And now instead of exit, what we would do here is we would, like in every function, call return. So this makes this function, which has so far been special and our main function and the only thing that was possible to call, has made this into a real function that anyone could call. But of course, we're not really using the call instruction right now. Now, one more thing. For this return instruction to not violently crash, like if I let this run now, I guess we can do it and see what happens. Oh, wait, it will get even worse. Yeah. Abort. So here's the thing. It might actually, the return instruction somehow crashed. But also, I'm actually surprised. I guess. Yeah. I think that's coincidence. Yeah, of course, because we partially initialize here. So we're lucky here. Everything else that we do not initialize here gets set to 0. So we're fine in that regard. But we were missing one thing, and that's why it crashed. And that is we do not have a return address or a base pointer to restore. So we crash. I guess we can run this in the debugger and see it. What does it say? Back called on empty vector. Yeah, we actually get the error message here. So that means our return instruction failed here. And why is that? Yeah, of course, because this return instruction expects that someone called the call instruction to set up, to push two things on the two stacks, the return address and the other thing. So for this to work like exit, what we actually have to do is we have to go here and say registers stack pushback 0. That's okay. Our base address outside, whoever called it is not really relevant, and 0 is fine because that means it's the first element on the stack, and the stack will probably be empty. And then we say registers return address stack pushback null pointer. Remember, null pointer was our special thing that we check here. If it's null, we're done. So that means we have to put these two at the bottom of our stack. And, of course, now, as call would do it, we have to do registers base index equals... Oh, we forgot that one. We didn't set, we only saved our base index. Okay, so registers stack size. And now we take this and also put it into our call instruction where we forgot it. Okay, here. So you see, we save the base index. Then we change the base index to the current stack size. So that means it gets its new, or rather, we have to do that here. So, well, we don't, but like if the return address stack again was part of the regular stack, we would have to set the base index afterwards because, of course, we have to account for the newly pushed base address and return address. But in this case, we could have actually done it right after only that pushback because that's a different stack. But again, so now it should run without crashing. Yep, done, you see? So that worked fine because now the return instruction actually found the two things it expected on the stack. And now it could call itself. The problem is just I would have to find a way to actually code that in a way that doesn't end us up in an endless loop. Because, of course, if it calls itself, then it will just eternally call itself. So what we would have to do is we would have to pass it parameters. So how do you pass parameters to a function? Well, it's basically the same approach. You push them on the stack. So here's the thing. You can only unwind the stack from the back. Or you can only take elements of the stack from the back. So what you would want to do when you call a function is you would push, the base pointer and the return address. And then the next... Oh no, actually, you would do that before. Of course, yeah. You would do everything. So you would move, let's say we have one parameter and a return value for now, which is all we need. So we put the return value first. This is because we want the return value to be the only thing left over once our function has returned, right? We want whoever called us to have that on the back of the stack, like we did with our addition instruction, you know? It takes the two things it was given and pushes the return value on the stack. So we need to leave that on. And then we also, so we reserve that space. And then we also, so that is the return value. Let's say that is 99. And 66 is our no, let's use 1 as our parameter, which is how often it should loop or something, which is what we will do with our main function once it calls itself, you know. We will just give it the number of times it should loop, and every time we call it, we give it 1 less or something like that. And then we can just that way make sure that it doesn't call itself once this number hits 0. So we've done that. We've reserved space and we've given a parameter. And then this will push again the base pointer and the return address, and we'll set the base pointer to point here. So base pointer will point here. And now we know that all our, so to find our parameters, we know we need to skip. So our variables start here. So here would be our x2. Let's get that one back just for order's sake. So here would be our x2, our variable. And we always know that to get at our parameters, we first have to skip the return address and the base pointer, the saved one, the old one, and then subtract, you know, like -1 for the first parameter. If we had 2, then -2 would be the second parameter, and 1 more than the number of parameters we expect is our return value. So that is -2 in this example case. So now you might be wondering, so why reserve space for the return value when in reality, you know, like in our add instruction, we didn't need to do that, right? We just, you know, pushed 2 things on the stack and then popped them again and pushed the result value. And that's simply because it makes it a little more convenient, because whoever calls you can just generate the code how they push all the parameters on the stack, and then they are the ones who will clean up again. Instead of your function having to clean up arguments. Now you might be a bit confused, like what benefit does that give me? Like, aren't I duplicating code? And yes, you could have a function clean up behind itself, but one of the advantages of this is, not in all languages, in some languages, like you have the current instruction, the stack pointer, and the base pointer, which, as you might remember, we called registers. So as we have these, some CPUs, rather not languages, have more registers, and those are called general purpose registers. Usually they have just a generic name, like, I don't know, A1, A2, A3, something like that, you know. And these are often also used to store parameters or results. That way you don't have to put stuff on the stack and remove it again. And especially for something simple like an addition, it's often much easier to just say, okay, I'll do all my maths with these few registers, and then I can just keep the result in there, and the next calculation I do will use that value again. And so, but even languages that have few registers usually have one register reserved for the result. And that means that all you have here are parameters. And that in turn means that you can add parameters to a function without having to recompile or the function, or you can remove them. You're a bit limited. You have to know that you're being called with fewer parameters. But, often that's just like an earlier parameter can contain a value that either indicates there will be 3 or 2 parameters, something like that. And the nice thing about that is that then, if in a newer version of your function you need more parameters, you can just react, like your function can just calculate, like since our parameters are backwards, so 1, 2, not 1, 2, as long as it only accesses parameter 1 and 2, it doesn't care if there's a parameter 3 above that, we'll just ignore it. So that means a program written for the new version of your function, and compiled for the new version of your function that takes 3 parameters, can call the 2-parameter version as well, and the 3rd parameter will just be ignored. But of course that means that the program has to clean up, because only the program knows that it passed you 3 parameters, while you only expected 2. So yeah, but basically you need to find some location for the return value, and by having the caller clean up, you are a little more flexible when the callee can change, so the called function. It doesn't really matter, you could do both. You could also make these functions behave just like you could also make the functions behave just like an operator. That would work as well. But anyway, one other reason is that really at this level, at the CPU level, there is not really a difference between a parameter and a return value, which in turn means you can have a function that returns 3 return values, as long as there's a fixed definition of how many return values it expects to give, it can just, you just push 3 storage spaces, reserve 3 storage spaces here for the return value. So of course you wouldn't push 99 here, you would just push 0 or something, and then when it returns, it overwrites the 0 with a 99. But you could return multiple return values. C and C++ don't really support that, but there are programming language out there that return so-called tuples, and a tuple is basically just multiple return values instead of just one. Or other languages just have the concept of multiple return values, and that's it. It's just a syntax thing. And of course, remember, in some C functions or C++ functions, you pass parameters by reference, which means you pass the address of a certain parameter instead of the value. So instead of 99, you would pass, or instead of 42, you would pass 0 here, and then the function would write its result into the stack slot 0. you know, that's something you could do. And here the thing is, you know, it might be helpful to have these still on the stack when your function returns, so that the parameter that returns a second value will still have the address here, and then you can call another function that maybe also needs that pointer, and you don't have to do anything to the stack. And you know, you kind of just save yourself all the unnecessary pushing and popping of stuff on the stack. But you know, it doesn't matter. For a bytecode interpreter, you can do either thing. It's just this is how many C compilers work. Usually what they do is they have the registers, so A1 or whatever, for, you know, an int16 return value. But then if you have a larger value, you know, say a string or something, then they will just put that on the stack. Or even in the case of strings, actually, you know, usually you allocate memory for them on the heap and then just pass the address, which again is just an int, so could probably go into the A1 register or whatever. But I'm going way too deep into this stuff again. So let's just go back and change our function so it takes a parameter. And now here's the thing, our run function actually, you know, would have to push something on the stack. So what we should probably do let's just say first argument and in 16, oh, it has to be in 16t, of course. In 16t pointer result. And by default, we set both of these to null. And now we need to, of course, include optional. All right, so actually we need it here. All right. So we don't need the include here because we already have it. What is it complaining about here? Redefinition of, oh yeah, of course. We only need the default argument in the declaration, not in the definition. Okay, and now we say if first argument has value, then registers stack pushback first argument. All right, and of course, if there is a result, if result, then register stack pushback, just reserve one slot for the return value. After we've saved the base pointer, of course, as in our graphics. And then here at the end, no, wait, it has to be before, of course. Sorry. All right, so first We reserve space for the result if the function needs one. Then we push the first parameter. It only supports one parameter right now. This is just a test case. You could, hand over an entire array. Actually, let's do that. Vector arguments, and then say for auto arg. No, wait, we don't even need that. We just say register stack insert stack end arguments begin, arguments end. That should be it, right? Let's see. Insert where first last. Yes, I did it in the right order. Okay, so just we can pass a bunch of arguments here, and it will insert them at the end. If it's 0, then it will just insert nothing. Okay. And of course, now here at the end, we will have to take if result, not registers, result. So if result is not null, then we've reserved some space. And then register stack 0. And result equals. So we're not using a reference here, but rather a pointer for the simple reason that you can set a pointer to null. Well, you can't do that. With a reference, only with a pointer. All right. So now run code. So this should be identical to our previous behavior. We're not expecting return value, and we're not passing any values as arguments. Let's see. Let's step into that. Not into the vector. Bytecode interpreter. There we are. So let's result is null. Arguments doesn't contain anything. Good. So now we create the registers. Look at it. Size is still 0 of the stack. No result. Insert call. Stack is still size 0. And now we push back the base pointer. Now size is 1. And now we push something on the return address stack. Yeah, that's also size 1 now. And now register stack size is the base index, so that means base index should now be 1. Yes, and it is. Now we can run our code or whatever. Run until the end. Result is still null, so we don't take anything off the stack. But the stack is actually still size 1. Interesting. Shouldn't that be 0 now? We might have a little... Oh, right, because... No, the return instruction... What is our... The return address stack is size 0. The current instruction is null. Oh, I think we're not cleaning up after us in the main function, are we? Yes. Okay, so one more thing we need is pop. Delete x. And we don't have a pop instruction yet, as far as I can see. So let's do that. Or let's call it pop int maybe. Pop int. Okay. So pop int should be right after push int. So pop int instruction here. Pop int instruction here. Hopefully I don't do anything wrong, otherwise those will all be misaligned. And now here. Pop in. See, that could have been bad, because if I hadn't realized that there was one too many here, then alright, so that just pops the last element of the stack. So if I hadn't realized that there were too many elements here, you know, what it just did is it set the return address not to, or not the return address, but the base index here. See, that was set to 10, which is the value of x at the end of the loop, instead of to 0. So yeah, this function wasn't quite clean to call itself yet, so we've avoided a bug here. Okay, let's go into run again. We can just keep that running. And now let's see, registers, stack size 0. Because the return instruction already removed what the call instruction, what we pushed in the call instruction stead. So those two are now gone again. And it restored the base index to 0. I mean, we could put any value in here really for the base index. You know, we could put -1 in here or something to, you know, make us reliably crash. Whatever we want. And anyway, if you look here, we're still 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, we're still looping 10 times. Nice. All right, so now we have the main function. It cleans up after itself, which we had forgotten. You know, that's basically, here we create x, so at the end here we need to delete x again, so that our function, you know, cleans up after itself. This is something the caller cannot do, or, you know, because what you want is for the, you know, you want to be able to change the internals of a function, like how many variables it uses for its algorithm or something, without having to change the caller. I mean, the caller could probably go like, I had this many variables before, and I expect one result, so I'll just, you know, pop everything off the stack until I only have that one result variable left. I guess you could do that, but it's kind of, you know, it's something this function can do much better, especially since, you know, maybe it needs no local variables, and then the caller would kind of be, you know, unnecessarily trying to calculate how much to clean up. So for efficiency's sake as well, you can just do it. Okay, so now what do we want? We want to call this with, let's say, the number 3. So 3 arguments. Oh, and remember the caller has to clean up. So what we have to do here is num argument equals argument size. So again, this is something that just our run function needs to set up for the first call here. So basically, usually that would happen in bytecode when you make a regular function call. And it will actually happen in a moment there as well. So num arguments, argument size, and then while num args minus minus. And then we do register stack pop back. So we just remove as many things as we've pushed, we remove again. That's it really. And since we push the return value before the parameters, we can remove all the parameters here and then get the result if there is one. So that's fine. All right, so let's see how this runs. Stop and rerun. See, argument size equals 1. So we have 1, num args equals 1, pop 1, and we're done. And if we look at the registers, yes, we don't have any extra arguments left. Wonderful. All right, so now we have our run function that can correctly call into bytecode and retrieve a return value. And you have, like, when you call run, you just have to know, does this return a return value or not? And how many arguments does it take? You just have to know that, what your bytecode expects. Which, you know, if you look here, you know, like the main function works like that. You know, it's always defined as taking a number of arguments and an array of that many arguments. And it returns an int. And that's all that your function has to do. Now, fun thing, if you remember how we pass arguments, and I said you can call a function that takes fewer arguments safely. This is where this is used. You can say int main void, or just int main in C++. You can even say void main. That's all valid. Why? Because when the system calls you, it basically does the equivalent of our run function. And so that means it pushes, like if it passed everything on the stack and not in registers, it would push a 0 on the stack for your return value, and then an integer for your argument count, and another integer, a pointer, actually, a memory address in an integer for your arguments that it gives you. And then it sets your base pointer to be behind those. So if you do never use them, you don't even know they're there. You know, they might just be valuable in a function that called you. And also, if you never set your return value, well, they pushed 0 on the stack, so they can just, it will just stay at 0 and will just assume, okay, your program execution probably was successful. You won't get like uninitialized memory and get like, 147, and then every time your app quits, you get an error message. So yeah, you also don't have to return 0 in that case. So that is one of the fun reasons why you can do stuff like this. Okay, so now we need to call us. So we're after the loop here, but before the end of the function. So every function ends with a statement that cleans up all its local variables and a return statement. This is different from this return statement. This return statement, all that does is it takes the 0 and assigns it to the memory slot that, where the result value should go. So that means whatever stack slot we pushed the 0 into or whatever. It will assign it another 0 in this case. And then it will jump to the actual end. So that means these two functions, like no matter how you exit this function, at the end, you will always go past these two instructions. So return in assembler is not the same as return in C. C eventually calls return and calls this. So when you generate code for this and you have a return statement, what you would do is you would say, you would create an instruction. Oh, we can use this one. You would say store int base pointer relative, and then you say so you would push an int before that, of course, to return, because store operates on. So let's put that in here as well, just for now. So you want to return the value 0. So we say load 0, and then we store int base pointer relative, and now it's important. We need to know where it is on the stack. So if we call this function with one parameter and a return value, and the base pointer is here, then that means -1, -2 to just get past those two saved value, the return address and the base pointer, or in our case that's just -1 because the return address is, of course, in a separate stack now. So -1. And then -2 to get past the parameter, -3 to get to the actual start of the result value. So that means this should be -3. That's where the return value goes. Return value equals 0. And then you would do pop int return. Like, you can do that every time. So this is a C return statement. You could do that every time, or you can just, go and put a jump by instruction here, which in this case would just be 0 because there is no code after this return statement. Return to, and these instructions here that clean up at the end of a function, those are usually called an epilogue. So that's like the outro of a book or something. And the one here that pushes the x variable, so reserves memory for the x variable, that's usually called the prologue. And so basically, we would say here return to jump to functions epilogue and actually return. Kind of something like that is what it would do. Oh, we could actually... Let's do that. Oh, it would probably be jump by 1, because we have to include the current function, right? The current instruction, because it doesn't automatically advance it. So we load, instead of 0, why not load 42? And now we say int 16t result value equals 0. And now we pass the result value. And say cout result colon all right. So let's print out the result each time. And now if I didn't completely goof, this should return 42, and we have 1 argument, so that's why -3 here should be correct. So now return value 42, and then jump to the epilogue, which, you know, this is a no operation. It just goes down by 1, but just for completeness sake. Let's see what happens here. I'll probably crash horribly. It actually, yeah, it seems to be stuck on something. Let's see. What did we do here? We'll probably never get there. Yeah, we're somehow already stuck. Oh, right. I forgot. We're jumping in bytes. Of course. Right? No, wait. Do we? Jump by. What does jump by earlier do? -12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. No, we're jumping in instructions. So that should really be fine. Oh, wait. Yeah, no, -3. So let's go and see store int base pointer relative is probably a good candidate where things could be going wrong. I hope this is of some entertainment value for you at least. For one, it will show you, you know, like everyone writes bugs. And for the other, maybe it's a bit entertaining because it shows you how I go about debugging things. So since we have functions here, this is actually really useful for debugging because we can just set breakpoints in them very easily and we can find them very easily. Okay, so let's go in the debugger. So the first time, oh wait, use of undeclared identifier arguments. Oh, maybe it didn't even build this time. Okay, a little bit confused now. Let's build and see if it builds. No, it builds. Okay, is it unhappy? Printed the number once. Oh, I think we're stopped at the breakpoint. Okay, so I don't know, this message might just be nonsense. Okay. Store. And now let's go in the debugger. Registers. Current instruction. This is just where we create our X, which is fine. And still here. Okay, so we have 10 times 3, 4, 5. Can we see our counter in the stack? 0, 3. Oh, do we have to? Oh, that might be right. 6, 7, 8, 9. 0 or 10. I think that's 10. What is the current instruction? Jump by -12. Okay, we're going back up the loop now. So if we go here and say open and write split and look at our code, we're now at this point. And now we're in the jump by instruction. Current instruction plus equals -12. So we're now jumping up. And that is now size current instruction is now load int base pointer relative. This one. So that means we're loading X with the next instruction. Load int base pointer relative, so push back. So our stack should now have 10 on it. Alright. So that means we should be at the last loop condition. So we will now push 10 and then compare them, and then we should jump past the end. And that's probably somewhere close to where it goes wrong. Okay. So we push 10. And now we should compare, right? No, wait, are we only now pushing 10? And now we're comparing, okay. So it grabs the 2 10s off the back of the stack and compares the difference, and that's 0. Bit confused. Oh yeah, right, the 10 is X. Right, because this is return value parameter and base pointer saved. So this is X. And now the compare is done, and the compare says it's 0. And now jump if 0, and that's the jump over the entire loop body instruction. So we get the 0 off the back of the stack, the comparison result, and it's 0, so we jump by 10 instructions. And now the current instruction points to push int 42, which is our return value. So that far we are correct. Okay. So push int 42, yeah, it pushed the 42. So now we should be store int base pointer relative -3. So our base pointer is what? Registers. Base index is 3. And -3 should be 0, which is our return value. That sounds good. So now we should store yeah, okay, we have a breakpoint here. So current instruction P2 is -3, base is 3, so that's 0. Register stack 0 equals register stack back and then pop back. Yeah, so now we have 0 set to 42. Registers current instruction. So you see, setting our return value already works. We know that now. Now we step to the next instruction, and that's jump by. Oh, and that's 0. Did we write the jump address in the wrong field? Yeah, I think. Yeah, we wrote it in the wrong field. That's what's going on. Should be here, and now it should work. So since we're jumping by 0, we're in an endless loop here because this instruction will not advance. That was it. Okay. And you see, yeah, it worked. So what we did now is we did our 10 loops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we returned 42. So that part works. Even with a little bit of debugging. All right. So let's remove all of those breakpoints. And now what we want to do is we want to actually look at the value we pass in, and that's 3. That's the parameter. So now in our bytecode, instead of going push int 10, we actually need to get the parameter. Load parameter 1. So we say push int no, it's load int base pointer relative. And that would be a -2. Remember, -1 is where we store the old base pointer so we can restore it when we return it. So what this does is, instead of taking a constant number of 10 loop iterations, it instead takes whatever the parameter is, which in this case is 3. So now we should get only 3 iterations. Does that work? Yes, you see, number printed 3 times, and then result is 42. And now, here we can actually call it again. And we say, first, we take load int base pointer relative -2. So push parameter 1 or load parameter 1. And then we say we subtract 1 from it. So, no, what is it? Add int. So parameter 1 minus 1. And of course, to do that, we need to push int -1, load -1. So these three statements should subtract parameter 1 from parameter 1. That is then the last element on the stack. Oh, and we need to push a 0. That's space for result. So we reserve space for the result. Then we calculate the number we got as a parameter, which in our case was 3, and subtract 1 from it. So that means it's 2. And then we call it. And now we have to know how far up we need to go. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So 17 minus 17 is the start of our function. So call ourselves. Now keep in mind, like in this case, you know, I know this beforehand. If you were actually generating code, you would just generate a call instruction here with 0 in the number of instructions to jump. And as you compile all this, you would just like, you would use a standard map or something to remember this like all the instructions that call, for example, the main function, if it's, you know, called, assuming this function here is called main because it's our first one. And so when they call the main function, then excuse me. So when they call the main function, you know, you would just have an entry in your table saying the instruction at this position calls the main function. And then once you're done parsing all this code, you would check, okay, main function, did we ever get a definition for that? Oh yeah. And then you loop over all these instructions and insert the difference between them and whatever position the main function is at. So it's the same as retroactively filling in the int. And in fact, what you could even do is, you know, you could put an actual pointer in there. I mean, here, this is an int 16, so not large enough. But otherwise, you know, you could write it directly into this instruction. And that's what a linker usually does. So that's the job of the linker in a real compiled program, is, or rather of the loader even. So the linker will just build this table saying these instructions call these functions that are not defined in this code. And then instead of using relative addresses, the loader would then like open your executable file, take this table, take other executable files, find out at what addresses their functions end up, and then compare names and say, okay, you are trying to call a function called main. In that code block over there is a function named main at address 5000, so I'll write 5000 into this call instruction. That's what the computer does. It's not magic. It's just keeping track of that stuff. And that is what an executable format. So I forgot what the Windows is. Windows called PEF, preferred executable format, or was that PowerPC? Anyway, like every computer, like macOS has Mach-O, the Mach object file format, and like every different Linux has ELF, executable and linker format or something like that. But anyway, all these things do is they are files that contain machine code, so like our bytecode here, as well as a table of functions that are not defined in that code, usually, system functions or functions from libraries, from other libraries installed on the system that it uses, and also usually the name of the libraries, so that the linker, the loader, will then know, okay, these other functions to get. The linker is really there for your code. So like you can have different source files, and each source file is one such array, and then the references between your source files are resolved by the linker and filled out immediately, because it just builds one huge block of all the stuff you link, and from that point on it knows where they are relative to each other and can just insert those relative jumps. But if you have dynamic libraries in there, or system libraries which are dynamic libraries, then it just needs to write down here, loader, fill that in later. All right, so now we are calling ourselves recursively, but with one less. Now there's one thing left to do, and that is we actually need to put this call in a conditional, because otherwise we'll still endlessly loop and we'll just have a negative number of loop iterations before we do that. Now, if this recursive call was actually in the loop, then we wouldn't have that problem, but I didn't want to touch the loop because then I would have to recalculate all of these offsets as well. So we're inserting a few instructions. First, we're inserting a instruction that loads parameter 1, and we will create one that pushes the 0, load 0, and now we'll make an instruction compare int less than, and now we need, so parameter 1, no, actually we need to do it the other way around. If 0 is less than parameter 1, so 0 less than parameter 1, that means we're good. We still have iterations to do. We've not yet reached 0, and because at the point where we reach 0 in our recursive call, we get an error. I guess I should write some equivalent code again. Imagine, so our function is void main int count, or That's the argument. And then what we do is we first do our loop where it's like int x equals 0. Don't we have that up here somewhere? Oh. X less than 10 plus plus x. And you know that does the printing, number printed, that you see here. Number printed, that's what that does. And then we do main count minus 1. That's what we want to do here. Okay? So, but what we want to, if we did this, it would just, try negative iterations and then call itself again anyway. So we need to prevent it from calling itself again. So we say if count bigger 0, or rather how we write it so we don't need a new instruction is if 0 is less than count, then call main. And that way, if we call this with 3, then it will call itself with 2, and then the 2 version will call itself with 1, and the 1 version will call itself with 0. And then that will print nothing. By the way, that should be count, not 10. And so that will loop nothing. We'll then check if 0 is less than 0, which it isn't, will not call itself again and will finally return. And so then we get out from the 0 call, back out into the 1 call, back out into the 2 call, back out into the 3 call, and then that will return completely. And all of them return 42. But we don't really do anything with that result. Makes sense, I hope. All right. So push int, load int, base pointer relative, and now we need to say jump by. So we're actually implementing our first if here. I only mentioned how you do that, but so if 0 is less than the count. Oh no, it's not a hard jump by, it's a jump by if 0, of course. Means 0 less than 1. That's true. And if it's 0, it's false. So if it's false, then we want to jump by 1, 2, 3, 4, 5, 6. Jump past recursive call. All right. So that should be it. And now we have to see. So that's an if statement without an else. It just, at the end ends up here. So I have to see 1, 2, 3, 4 instructions. So 17 would be minus 21 to call ourselves. And now this will be interesting because now we have our first call instruction. So I'll set a breakpoint in the call instruction. And now I guess we'll just risk it and run it, right? Oh. We are in the call instruction. Okay, good. Let's look at our stack. So, return value of the outer call. 3. That is the parameter, and then the base pointer. And then here we have our 3 iterations that have already been printed. So that's correct. So that's our x1. And then we've pushed 0 for the return value of this call and 2. which is, 3 minus 1. So that makes sense. That's the argument and the return value. Of course, now I realize I forgot something else. So we'll have to fix that first. Because what we didn't do here is we didn't clean up behind the call. So we need to add 2 more instructions. Pop int pop argument or parameter. That's what we called it here this time. Pop result. Because remember, we pushed that stuff, and we as the caller are responsible for getting rid of the space reserved for the result and for the one argument where we subtracted 1. Otherwise, won't be clean. So, okay, we added those 2, so that means 21. So that must be 20. No, wait, 21 is fine. The jump statement, where is it? Jump by 0, 6. That has to be 8. Okay, stop that again. And let this run once more. And now let's see. Stack. I think here it should be the same. We have 0 and 2. We call. So we push the base index. Yeah, that's 3. We push the return address on the return address stack. Yeah, we now have 2 functions in flight. Now we set the base index to our stack size, which should be 7. And where is the base index? Here, 7, yes. So now this function call knows what it can do. And now we jump back to the start. And that should be, the first instruction is a push int 0, 0. So if it's not that, then we have a mistake. Current instruction. Ooh, it's 1 too little, I think. Load base pointer, int base pointer relative. 0, 0, yeah. So I miscalculated, and the jump back up is actually where is it? Call here, 21. That should actually be 22, I guess. All right, and now please work. What happened? We're in the call instruction. So we've seen that this mostly already was okay. Base index is 7 now. Current instruction. Push int 0, 0. Okay, so we're at the start of our function where we want it to be. I should probably show you that in the right split again, just so it's a little more visible. I'm sorry that I'm partially covering something here. But so we are here at the call instruction. Or we were here, and now we jumped back up all the way to the start. And now let's look at the console. Can I type here? Yes, I can. Okay, and now let's see what happens if I just step through that code at some point. Oh, I should probably just be able to let this run And we should be to the next call. Now you see it printed 2, and then we're at the call instruction again. So it seems as if it's working. Again, go in here. Current instruction is push int 0, 0 again. So again, we've jumped from the call instruction here with another set of variables. And if you look at the stack now, should have the same as we had before. Yes, 7 is the saved base pointer. 1 is the how many iterations do we want, and 0 is the result of this call. In our return address stack, we have 3 return addresses now. And now we let this run. And now we have the, okay, I should have written another, yeah, I can't anymore. So there should be another XXX here. So you see that this is just a single, because as you know, we had 2 already there. Now it just did 1, and we're in a call instruction again. And now we're in the call 0 case. As you see, we have 0 as the return value and 0 as the argument. We push the base index, which is now 11. We save that. And again, now 15 is the new base address. Right? Yeah, 15. So that's the 0 case. And so now we should not end up in a, we should get, let's see, yeah, we should get here, and at jump by, if 0, we should jump past the recursion and end up here. I'm trying to think if there's a good way for me not to step through all of this loop. Oh, well, the loop is 0. So I guess we can step through it. It shouldn't be taking too long. All right, so current instruction is push int 0. That's what it does. Next instruction is what? Load int base pointer relative. Okay, and after that, yeah, and now we're here at the load int base pointer relative. That's fine then. And now we should be at the compare instruction, yes. And the stack for the compare instruction has a lot of zeros. So 0 less than 0. Nope. So this should jump past the entire loop and land us here, I think. Yeah, here, right at the start of the call instruction. So let's see if that happens. Oh, that was just the compare, of course, and that returns 0, which makes sense. And now we jump, and we're landing at a push int 0, yes. So now, load int base pointer relative -2, that's this instruction. So we're now going through the conditional of our if statement around the loop. I'm going through that a little bit faster. Compare. It's return 0 as well. So now jump by if 0 should lead us past so 8. 1, 2, 3, 4, 5, 6, 7. Push int 42. Yes, we're here. Okay, so now we're loading the results. So that worked. We didn't recurse again. So that means if I now continue, we'll end up in the first return. That will unwind. We'll end up in the second return. And as you see, it's already gotten, our stack has already gotten shorter. It's only 11 elements long now. Now we're back at 7 elements long, 3 elements long. And that's it, I think. No, yes. And now you see result 42 done. Good. So that means what we just did is we actually executed an entire recursive function call, 4 calls deep, I think. 3, 2, 1, 0. 4 calls deep recursion. 4. All right. This, I'm sure this is much or something. I will push this to the GitHub, so you will have the full code. If you're interested in the older code for one of the previous episodes, you know, you can go back in the history of the Git repository to see that. The link to the Git repository will, as always, be in the description under this video. So yeah, is there anything else we need to do? Not really. So yeah, I think this is a good point to end it at. I have no idea how long this video turned out. I don't have a running tally and I didn't look at the clock. I hope it's not too long. But anyway, so yeah, it's actually surprisingly, it's 4 instructions, 4 new instructions that we introduced to allow for recursive function calls. And as I said, you know, if you didn't need recursion, you might not even need the base pointer relative. Well, no, you still need the base pointer relative stuff because one function can call another, and of course there you need the base pointer as well. Sorry. But anyway, thank you for listening. I hope it was helpful to some of you. I just don't like this extra. Here, yeah, there's 2 returns in there. We don't need that. We only need 1. Okay, let's just let it run once more. As you see, 1, 2, 3, 1, 2, 1. And 0 doesn't print anything. And we can return a result from a function as well. And of course, all of this is optional. Of course, if with this bytecode that actually returns data here at the end, with this -3 offset, I cannot call this without passing result value here, because then it wouldn't reserve space on the stack for it. And that's the dangerous part in, also if you do this in assembler, by the way, like if you call a function recursively, you know, it expects stuff to be in certain places, and if the caller does that wrong, it won't work. If the caller provides more guarantees, you know, that's fine. So for example, with registers, this can be very dangerous because registers are there. So you do not, like, there is no, well, in general, you often don't crash if you get anything wrong here, because, you know, it's just, because you're just overwriting someone else's memory. And usually the stack is not right at the start of memory. So if you underrun the stack, by doing -3 when there's only 2 elements, then you just write over some bytes that are there. Maybe they're not used, then you're safe. Maybe that's a previous function stack, a previous threads stack, or maybe that is heap memory that is used for, keeping the user's text or something. And then you've overwritten that, but you don't really see it until someone else tries to view the text and says, why are there random bytes at the end of this text? That's the issue. And of course, the same for the arguments. What programming languages do, many scripting languages, for instance, can actually tell how many parameters you passed, and you can query, and you can even get a variable number of parameters. What they basically do is just that one of the parameters, like the first parameter, is always how many parameters did you expect, or did you get. And in that case, of course, the return instruction could just clean up those parameters at that point in time. That's totally valid and worthwhile to do in such cases. You can do the same even for result values if you pass them on the stack. Or what other languages do is they just pass an array, because an array implicitly has, if an array in that language implicitly starts with like the number of elements in it, and then the elements, then you can just use that. If you're pushing that stuff on the stack anyway, then there's really not much difference. It might be like the count is basically an extra parameter, and that's it. And that leads itself to some really nice high-level programming approaches, where you can just ask, like if you have a sum function, you can just let the user do sum A, B, C to summarize the variables A, B, and C together. And, no matter how many variables they want to build the sum of, it works, and they don't have to build an array themselves, so to say, because the compiler will just do that. So it's a convenience for writing. All sorts of interesting things can be done with that. But anyway, again, I'm getting off the point. We called a function okay, we called a function here. Actually, that's the same file. So yeah, that's what this function looks like in our bytecode. And that's the original code we ran right at the start. Push 2 numbers, add them, and print them. We could probably even, like do a, I don't know, print 2 ints function, and then do, like print the number of the iteration each time to make it nicer. But that's left as an exercise to the reader, because I don't want to fuck around and change the loop condition names and things like that. And that's, by the way, so for those of you who want a fun exercise or something that they can do next, this is kind of, writing code like this is kind of annoying. What you can do is you can write a program that is an assembler. What does an assembler really do? Like, you've heard of assembly language and machine language and an assembler. What's the difference? Well, machine language is basically the bytes that come out of this. Well, that's bytecode, but like if we weren't writing bytecode for a simulated CPU, but we're writing real machine code for a real existing CPU, then what comes out of this would be the machine code. And that's basically also just structs, Then assembly language is a programming language that is really close to this machine code. Basically, this is almost assembly language. Because what you do is you have the name of the instruction, which is the name of this constant. And then you have one argument or two arguments or something like that. And here in our case, you could actually, you could just write a simple program that opens a text file, takes the text, scans the first word until the first space or comma or whatever. Space, I guess, usually in this case, not comma like here. And then looks that up in a list of names, then it would be, push E or something like that, push I or something like that would be the first, would be equivalent to the push int constant. And then it would just write push int into the instruction struct. Then it would see, is there something following that, or is it a line break for the next line? If there's something following that, then it scans until the next space or line break, and it takes that as a number. That's parameter 1. If there's then a comma, it scans again and gets parameter 2. And then if there's a line break, it goes to the next line. And that way you could basically write only these. Wait, I pushed the wrong button. These things here. Without the curly brackets, without the instruction and things like that. Just the actual data. You can write that loose in a text file and it will look much more readable without the other noise around it. And then, of course, you can get fancier and say, okay, if there is a semicolon anywhere on the line, that's the start, or 2 backslashes anywhere on the line, that's a comment. Usually in assembler, they used a semicolon for some reason. So that's something you could do. And that way you can write yourself a little, very, very simple programming language that lets you write assembler code. Why would you do that? Like right now, that's not really an advantage over doing it here in line, apart from having separate files, and not needing to run GCC every time you change your program. You could then just, take the array that program that you wrote generated and feed it into run. So why would you do that? Well, the cool thing about that is that, for example, for the loop addresses, what you can do is you can say if a line starts with text and then a colon, so a label like we have it in C, like main colon push int 0 load int base pointer relative 0, kind of like that. You could just write that code and you could say, okay, if I encounter colon, then the first word is not the instruction name, but is actually a label. And then you can just go, okay, I'll take the size of my array into which I write the instructions and save that under the name main in a dictionary. And then whenever someone does, for example, a call instruction and writes, they can directly write main there instead of a number. And so if it's not a number, you take whatever the current size is and the contents of that label and write that in there instead. Or rather, you make a note, someone here wants the contents of, so not here, but like in the call instruction. Again, you generate the call instruction with, if someone writes call main, you generate a call instruction with 0 in it, and in the entry that says main is as this at this and that address, you write the position of this instruction. For main here, that makes less sense. There you already know where it is because you've already seen it. But if, for example, you had a second function, foo, that does something else. Load int 42, whatever. And you call foo here. Then of course you can't see that yet, you don't know it. So you just make an entry for a function named foo and write that the instruction at offset 0, 1, 2 in your code array references foo. And then once you find foo, which is 0, 1, 2, 3, I guess, then you loop over everyone who has been registered and insert in this spot the difference between its index, so 3, and foo, which is in this case 4. Of course, there would be more instructions below here, but you get the idea. So it's basically the same retroactive filling out that you use for if-then and things like that. And the cool thing is, once you have these labels, this code down here becomes much more readable, because the magic here, the 10 that jumps past the end of the loop, turns into loop end as text, and then here somewhere a label loop end. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so here it would just say, loop end instead, and instead of 10 it would say loop end here. So that would actually turn this thing into almost a programming language, which, assembler is basically a very, very simple programming language. It's sort of halfway between, I guess, a markup language, because it just describes the bytes of your machine code in text form, but it has these 1 or 2 extra things where it, most assemblers know that, push int doesn't use parameter 1, it only uses parameter 2. So it will just, it just lets you say push int 42 or push int 0 and it will know that that's parameter 2 and not parameter 1. So you can make it a little smarter. Now you might think, if I want to build a compiler, why build an assembler for the bytecode machine? And that's the cool thing. I always recommend build an assembler for your bytecode, for the simple reason that then you can do unit tests. Because you can just go and say, hey, this code should work as is. So just copy this code into a text file and then write a little script that takes the built version of the rest of this program, which is basically a call to bytecode interpreter run, and code that loads this array from a file. And you can just take that built assembler and run it over each of these source files. And if you ever make a change that breaks something, it'll immediately, one of those source files, which contains all the test code like this one that you use during development, will fail to work and will give the wrong result or something like that. And then I broke something. And that just makes for a much more stable programming language. You can just test every small command, write a program that only contains push int. And then, only push int is maybe a little difficult. You need push int and then store int base pointer relative -2, I guess. You don't need a parameter. And then return or whatever. And then the result should print out whatever int you wanted to push. So 42 or whatever. And that way you can just write a little script that, checks all these results. You can even, what I usually do is I have 2 text files. One with the assembler code and one with the output I expect to get from this assembler code. And then I just make sure that all of this either returns a value or calls print int or whatever equivalent, my language has a print command. And that way, you can, it's a lot harder to break your programming language with a change for new feature B, because you didn't test again whether feature A still works, and then you realize, oh, I changed the way this instruction does things a little bit, and now it doesn't work anymore. So yeah, and that's it for today. Thank you for listening, and I hope it's helpful for someone. I don't know why people are listening to this, but I'm happy to make more of these recordings. Thank you, and bye-bye. Have fun coding and making your own programming languages.